Okay, so now getting back to current, remember that there were two things that we said are going to affect the amount of current in a circuit. One is the resistance that is attached to that circuit. So that's where we're talking about things like, is it have a longer length, bigger cross-sectional area, what materials are attached, what's the temperature. So all of those things are going to affect the amount of current. But the other thing that's going to affect the amount of current is the potential difference of the battery source. So those are the two things that are going to also affect the current in the circuit. So these are separate from each other. The potential difference comes from the battery. The resistance is what's attached. But together, those two things are going to determine how much current there is. So we're going to try to find some relationships to see how does resistance change the current and how does potential difference change the current. So if we're going to take a look at this simulation and gather some data quickly, so just put this here so you can see, this is my battery, this is my resistor, and then this is showing me how much current is in the circuit. So I'm just going to make a quick chart here. I'm going to put my potential difference here. The unit for potential difference is volt. Then I'm going to put my resistance. The unit for resistance is ohm. It's a Greek letter that looks like that, and the word that you say is ohm. And then current is measured in amps. So we're going to take our simulation and again record some data here. So I see that right now my battery is 10 volts, my resistance was 10 ohms, and my current was 1 amp. So now I'm just going to make some adjustments to this. Instead, I'm going to make, I'm going to keep the battery the same, but I'm going to play around with the resistance and see what happens to the current. So I'm going to change my resistor over to 20. Let me just move this over a little bit. There we go. And you can see as I'm changing the resistance, the current is continuing to go down. So now I have a resistance of 20 ohms. That's the ohm symbol I was referring to. And there is your amount of current. So if I have a 10 volt battery, but I double the resistance, I see that the current is now only half as much. So more resistance is making the current decrease. So I'm going to take my same simulation here and I am going to change the resistance to another number. So I'm going to change it up to 40. Just sliding it over here and I'll slide it over in a second. So now you can see when it is at 40 ohms, the current has decreased again and it's all the way down to 0.25 amps at this point. So I'll go ahead and record that data. So again, I kept the potential the same, but I increased the resistance more and I can see the current has gone down even more. So I can make a note over here that as the resistance goes up, the current is going down. If it's twice the resistance, it's half the current. 4 times the resistance is a quarter of the current. So that tells me that this is an inverse variation. So I would expect to see that when I write out my equation in a second. Now what I'm going to do is instead vary the potential difference. So I'm going to vary the potential difference and I'm going to double it to 20. And I'm going to set that resistor back to 10. So I'm just going to make those changes really quickly. So my resistor, I'm going to put back to 10. You can see what I'm doing here. So I'll set my resistance at 10. And I'm going to set my potential at 20. And you can see what I end up with is a current of 2 amps. So I have doubled my potential, keeping the resistance the same from this first line, and I see that I have doubled my current. So now I'm going to try tripling the potential difference. Again, I'm not changing the resistance, I'm changing one thing at a time. So I am going to triple the voltage of the battery, or the potential difference. And you can see that when I triple it, I end up with a current of 3. So as expected, when I tripled the voltage, I also tripled the current. So when the voltage goes up, the current also goes up, and that is a direct variation. So based on that, I should be able to get an equation out of this. The current is equal to, well, I see an inverse variation here. That means resistance must be in the denominator. And this is a direct variation, which means delta V must be on the top. And if I check this relationship quickly, 10 divided by 10, so if I take this over this, delta V over R, 10 divided by 10 is 1, 10 divided by 20 is 0.5, 10 over 4 is 0.25, 20 over 10 is 2, so you can see each time this relationship is working. And this equation is what is called Ohm's Law. So we have this relationship for Ohm's Law that says current is directly proportional to potential difference and inversely proportional to the resistance. What we often do, though, is multiply the R to the other side, and this is the way that we typically write the equation, just in a more user-friendly format. Again, really it's the current that depends on these two things, but we often write it this way just for ease of calculation. So on your formula sheet, please go ahead and add this equation right here. So put delta V equals IR onto your formula sheet. And you will see this little triangle. It can just be helpful. If you want to solve for V, you multiply IR. If I want to solve for I, you divide by R. So I would be V over R. And if I want to solve for R, it's V over I. So if writing the triangle like that helps you visually see that I is V over R is V over I, and so on, you can certainly use that as a tool to help you. Last couple quick things to look at is how a lie detector test works. Basically what happens is when you tell a lie, your body will sweat. And when you sweat, what happens is you have excess moisture and salt on your skin, and that will increase your own conductibility. Your resistance, in other words, goes down. So what happens with this equation, your resistance goes down when you tell a lie because of that perspiration, which means the current that you have been connected to will go up. Now, not so much that you get zapped or anything like that, but the current increases by a small detectable amount, and that helps indicate that you could be lying. Finally, you've probably heard of superconductors before. A superconductor is something where the resistance actually goes to 0. There is actually no resistance whatsoever, but only at or below a certain temperature, and this is a very low temperature. This includes really common materials like aluminum, zinc, lead, tin. I think we think of superconductors as some kind of crazy made-up material, but these common materials are actually superconductors. And the reason that these are important to us is once a current is established, if there's no resistance, it's like Newton's first law. If there's nothing to force something to stop, it'll just keep going. So if there is no resistance inside the wire at all, once those electrons are made to go, there is literally nothing stopping them. They will go forever. And a constant current without any battery or power supply is really intriguing to us. But again, this only works at very low temperatures. Right now, one of the highest ones we have, or the lowest temperature the highest low temperature we can get to is about 103 Kelvin. That's negative 220 degrees Fahrenheit. So we're talking really, really low. But this graph shows what happens for a superconductor versus a non-superconductor. As the temperature goes down, the resistance is going down. That's why the graph goes this way. And it actually goes to 0 below this certain temperature, whereas non-superconductors will maintain some level of resistance. And we use this with something called the Meissner Effect, where electric currents can produce magnetic effects, and this interaction can cause a magnet to float over a superconductor. So you may have seen trains like this. I know some exist in Japan, where it's a superconducting train. So the train can go very fast because there's no friction. It's literally levitating. And they're also looking for potential use, perhaps with power lines.
So tomorrow, I'll do the activity. however long it takes.